I'd like to talk about saving for a bit. The UNROM512 mapper I'm using for my NES projects handles saving in a very different way than the battery-backed SRAM approach that certain classic NES titles had. The actual program ROM data is written onto a flash memory chip instead of being baked into a mask ROM package. So what we can do is actually overwrite sections of our program data on this flash memory, and we can easily use that to store persistent save data on the cartridge. Now on these particular NOR flash memory chips, we normally have to erase the data that's already there before we overwrite it. And that's because the result that actually gets written ends up being the bitwise AND of the data that's already there and the data we're trying to write. So any bits that were already zeros in flash memory will remain zeros no matter what value we write to it. And that effectively makes it so that the only changes we can make by writing data to flash is clearing bits to zero. Now these chips have a function to erase sectors of flash, which is basically just resetting every bit in that sector to a 1. The size of the sectors depends on the chip package. The chips I'm using are part of the SST39SF series, and their sectors are 4 kilobytes each in size. I've seen other chips that have up to 64 kilobyte sector sizes, but in my case, the smallest portion I can erase is a 4 kilobyte section of flash. Now in comparison, the actual size of my save data is only 18 bytes, and it sounds pretty wasteful to have to allocate 4 kilobytes to something when you're really only going to use 18 bytes of it. But there's another thing to keep in mind too, which is that these flash chips are really only rated to handle around 100,000 erase cycles or so for their whole lifetime. So ideally, we want to delay having to erase sectors whenever possible, and when these sectors do eventually become unwritable, we probably want some sort of failsafe to make sure the game can still be played properly. So the idea came up to split the 4 kilobyte sector into smaller chunks, and whenever we save new data, we just write to the next available chunk without needing to erase the whole sector. Now to address which chunks are already written to, we can set up a sort of header to keep track of each chunk's status. Remember that writing data to flash memory is always the bitwise AND of the value we write and the value that's already stored. So when we overwrite a new save chunk, we can tally off the corresponding bit in our header by clearing it to a 0. So any bit that's a 0 in the header means that its save chunk has already been written to, and any bit that's still a 1 means it's free. And so the only time we actually have to erase the entire sector is when this header is completely tallied off and all the save chunks have been overwritten. I ended up using a 16-byte header, which would let me represent 128 save chunks in a sector, each of which are 32 bits in size, and 32 bits gives me a little wiggle room for expansion if I need it. But to also fit the header in the 4 kilobyte sector, I had to sacrifice one save chunk, so it's really 127 chunks I can address, which is still plenty. We can still use that most significant bit for something, though, as a sort of flag. I've actually set up 2 sectors for save data, and together they kinda act like a double buffer. Once the main sector fills up with valid save data, the other sector gets erased, and we start writing our save data there instead. And we just keep switching back and forth when a sector gets completely filled. So when a sector inevitably dies and our write verification checks fail, assuming our program can recover from that, we can default to our other sector and prevent saving any more data from here on out. So we'll always have some valid save data to load from in the event of a sector failure. If I wanted to add some extra metadata, we could also do something like alternate between sectors on every save, but I decided not to mess with that or go that route. So here we are in game, so I can demonstrate this a little bit. I have things set up so the settings autosave when changing screens, and only if the data has been changed from the last save, so we're not just constantly autosaving unnecessarily. And as you can see, every time we save new data, it moves on to the next chunk in the sector. These red values are writes, and the blue values are reads, for the record. The corresponding chunk flag in the header is cleared, and we didn't have to actually erase the sector, so that's good. If I modify the header a bit so that we're at the end of the sector, and I keep saving data, the alternate sector gets erased, and the new data is written there. And as we keep saving, we keep going through the chunks in that sector until we're at the end, and then we can erase the main sector and do the process all over again. And of course, we have some data verification checks in this whole process. With our header, we're iterating from the least significant bit to the most significant bit. So we know that it should be a contiguous set of 1s and then a contiguous set of 0s. If for some reason we get a 0 and then a 1 again afterwards, we know that the header has been corrupted. So if I intentionally corrupt the header here, we should get an error. Here I've set up an error handler screen for autosaving. It lists what sector was affected and correctly states that it's a corrupted header error. I have a few other error states it checks for. One just reads the data byte just stored to flash and checks if it's the byte we actually wrote to it. Another is for sector erase, where it reads every byte in the sector and makes sure they're all FF after an erase command. In other words, when all the bits are set to 1. But the last thing it checks for when we're overwriting a save chunk is a valid CRC value. Now, cyclic redundancy checks are a common method of verifying data integrity, and here the beginning of each save chunk gets a CRC value calculated from the rest of the save data. Now, CRCs are a whole other topic to get into, but in the end, I've settled on using a 9-bit polynomial, which calculates an 8-bit result, and that makes the process of calculating the CRC a little simpler on the 6502. The polynomial value I chose has a Hamming distance of 4 for data lengths up to 30 bytes, and this can help catch errors that might slip past the corrupted header check. So if I corrupt the header like this, so that the most recent save chunk is one that doesn't actually have proper save data in it yet, we should get an invalid CRC error, and we do. So at this point, I'm pretty satisfied with this autosave system, and hopefully you'll never have to see these errors in practice.